Okay. So we were discussing. Ashi, can you sit straight? So we were discussing induced magnetism. Now, what is induced magnetism? When a magnet is brought near a magnetic substance. For example, this is a magnet. This is the North Pole. This is the South Pole. This South Pole, and this is a magnetic substance. Now, this magnetic substance is brought closer to this magnet. So what happens is that this South Pole will induce a pole over here. So this South Pole will induce a North Pole, opposite polarity. Okay. So यहाँ पे एक temporary magnet बन जाएगा with the South Pole. That is called induction. Okay. Now, since their poles are opposite poles attract each other. ये दोनों एक दूसरे को attract. समझ में आई? So what happens first, induction or attraction?
Attraction.
Attraction. Janvi? Can you write? Dhyan? Dhyan, can you switch on the camera? Why I have to tell you so many times?
Ma'am, my camera is on.
क्यों मुझे तो नहीं दिख रहा है? आशी आपको दिख रहा है?
No.
Correct, Janvi. Dhyan, what is the answer? Attraction or induction?
Attraction.
How? This is the North Pole. This is the South Pole. When a magnetic substance comes here, what happens first? Opposite polarity is induced. So पहले क्या हुआ?
Induction.
Induction. Induction होने से opposite polarity आया, opposite poles attract each other, फिर attraction.
Okay, ma'am.
Everybody understood? Okay. So, and this induced polarity is permanent or temporary? Temporary, because it is there as long as the magnet is there. As soon as you remove the magnet, it will also lose its magnetism. The temporary, the magnetic substance will also lose its magnetism. So a magnetic pole induces an opposite polarity on the near end and the same polarity on the far end. And induction precedes attraction. Abhi samajh mein aaya why induction precedes attraction? Because first an opposite polarity is induced. After that, the attraction happens. So induction precedes attraction. Now, induced magnetism is temporary. It stays as long as the cause is there. That is, the magnet is there. As soon as you remove the magnet, the magnetism is also lost. Okay. So the magnetism acquired by induction is purely temporary. This you can check it out if you have magnet. I don't know where my magnets are all gone. So otherwise I would have shown you. So if you take a magnet and you start sticking the iron nails. So magnet है यहाँ पे, ये magnet है, ये north pole है, यहाँ पे एक iron nail लगा है, उसके नीचे एक और. So this you can stick the iron nails till a considerable length. Why? Because ये north pole था, तो induced south pole आया, south pole के opposite में north pole आया, फिर उसने दूसरे में induce किया because each one is having temporary magnetism. फिर जैसे आपने ये मैग्नेट हटा दिया, वो सारी iron pins जो nails है, they will also get scattered. Okay, so look at the figure 10.3 in magnetic induction. So north pole is having south pole towards it, फिर north south ऐसे करके induced magnetism की वजह से you can so many nails get attracted. Okay. So as soon as you remove the bar magnet, all these nails will get scattered. Now, lines of magnetic field. So temporary magnetism acquired by magnetic material when it is kept near or in contact with the magnet is called induced magnetism. The magnetic pole an opposite polarity on the near end and a similar polarity on the farther end of the iron bar. Induction precedes attraction. Induced magnetism is temporary. Now, lines of magnetic field. The space around a magnet in which the needle of the compass rests in the direction other than the geographical north and south direction is called magnetic field of the magnet. The magnetic field line is a continuous curve. So now what is the magnetic space or magnetic field? So अगर आपने यहाँ पे एक magnet रखा and you bring a magnetic compass, अगर इसमें magnetic compass लाओगे तो magnetic compass will always point in north south direction, ठीक है? But जैसे you bring a magnet near it, this magnetic compass will point in a direction opposite, in a direction different than the geographic north and south. So this direction of the magnetic compass now is showing the direction of the magnetic field. And this compass is not aligned to the geographical north and south because of the magnetic field. Okay, so now what is magnetic field? It is the field around the magnet. Where it's a field around the magnet where the compass, the middle of the compass rests in a direction other than geographical north and south. So it's a space. Okay, so it's a space. So magnetic field, the space around a magnet in which needle of a compass rests in a direction other than the geographical north and south direction is called magnetic field. So it's a space. Okay, so magnetic field is a vector quantity. The magnitude of the magnetic field at a point is measured by a force experienced by the magnetic pole of unit strength placed at that point, while the direction of the magnetic field is the direction in which the north pole of the needle of the magnetic compass rests when it is placed at that point. So these are very important things. So magnetic field is a vector quantity, and how do you find the magnitude of the magnetic field? That is measured by the force experienced by the magnetic pole of unit strength placed at that point. How much force is being applied? So while the direction of the magnetic field is the direction of the north pole of the needle of the magnetic compass. So when we place a magnet above the sheet of a stiff paper and spread some iron filings and you tap it, so you get this kind of arrangement 10.4. So arrangement of iron filings over a magnet shows the magnetic field of the bar magnet. So it automatically gets arranged in this form. Now, when you see, look at figure 10.4. Look at this figure. So you can see there are continuous closed lines. Can you see these lines? So these lines are magnetic field lines. So these magnetic field lines are continuous curves in a magnetic field such that a tangent to any point of it gives the direction of the magnetic field at that point. अगर हमको direction पता करना है, so we have to draw the tangent to that point. Okay, so magnetic field line is a closed continuous curve. You see, these are closed lines and these are continuous curves.
Yes, ma'am.
So properties of magnetic field, they are closed and continuous. These are very important. You have to know at least five properties, and questions are asked on all these properties, so you should be knowing them. So they are closed continuous curves. They go from north pole to south pole outside the magnet. Outside the magnet, they travel from north to south, and inside the magnet, they travel from south to north. Okay, inside the magnet, they will travel from north. Outside the magnet, they travel from north to south. A tangent at any point on the field line gives the direction of the magnetic field. You know what is the tangent? Anyone who knows the tangent can
Yes,
answer.
ma'am.
Yeah?
Ma'am, tangent is a line which goes through, a tangent is a line which goes outside the circle, touching the circumference point.
Yeah, a tangent is a line that touches the circle externally at one point, and it doesn't pass through the circle.
No,
Okay,
it
so
doesn't
it
pass.
touches the circle and goes. And so the direction of the tangent will give you the direction of the magnetic field. And these magnetic field lines, they never intersect each other. Very important point, mark it. These magnetic field lines will never intersect each other because they all are moving in a certain direction. If they all are moving in the same direction, they will be parallel, but they cannot cross each other. They are denser at the poles and separated at the middle. If parallel and equidistant, they are uniform. Now, they behave like a stressed rubber band. Let us go back to the figure. Look at this. These are magnetic field lines. So they are starting from North Pole, going to the South Pole externally. Okay. Now these field lines are closed continuous curves. And look at a very, very small part. If I take a very small part, let me take this part. Let me take this small part. Can you all see this small part which I have taken?
Yes, ma'am.
Yes, ma'am.
So if this small part, you just check, these small lines are almost parallel to each other, correct?
Yes, ma'am.
Because the magnetic field is uniform, these lines are parallel to each other. Okay, so same thing happens for the Earth's magnetism. अगर आप एक particular जगह का आप लोगे, so एक particular जगह का आप लोगे, for example, आपने वापी का एरिया लिया, उसमें भी आपने अपनी सोसाइटी का एरिया लिया. So Earth is a huge magnet. So Earth's magnetism is also there. And so if you take a small space of the Earth, then these magnetic field lines will be parallel over there. So Earth's magnetic field lines at any point are parallel because the Earth is a huge space. And for if we check the magnetism at a small area, in a small area, the Earth's magnetism is uniform. Okay, and that is why we see parallel lines. So a freely suspended magnetic field always rests in geographical north and south direction. An iron rod buried inside the Earth along with north-south direction becomes a magnet. And neutral points are obtained on plotting the magnetic field lines on a magnet. Now, what are these neutral points? Neutral matlab, there is no charge, right? Neutral, so no polarity. Now, what happens? Neutral point में क्या होता है? Earth's magnetic field is also moving from that space. And वो magnet की वजह से there is also a field line. So these two field lines, they cross each other and they nullify each other, and therefore there is no magnetism felt at that point. So at neutral point, if you bring a magnetic compass, the magnetic compass will remain as it is. It will neither align with the Earth's magnetism nor it will align with the magnetic magnetic field of the magnet. Okay, वहां पे जिसको जैसे घुमा के रखोगे वो magnetic compass will stay as it is. Okay, so a freely suspended magnetic field always rests in geographic north and south. An iron rod buried inside the earth, along with north-south direction, becomes a magnet after a long period of time, maybe 2-3 months. A neutral points are obtained on plotting the field lines. So these are the evidences that Earth is a huge magnet. Earth is a magnet. A magnetic needle rests making different angles with the horizontal plane when suspended at different parts of the earth. And magnetic needle becomes vertical at poles, magnetic needle becomes horizontal at equator. In limited space, the field lines of the earth parallel. This is very important, as I told you. In a limited space, the field lines of earth are parallel and equidistant. Give reason. Why? Because Earth is a huge magnet, and if we consider a small space, the Earth's magnetism is uniform in that space, and that is why we get parallel and equidistant field lines. Is this clear? Did you people note it?
Yes, ma'am.
In a limited space, the field lines of Earth are parallel and equidistant because Earth is a huge magnet, and in the limited space, the magnetic field lines are the magnetic field is uniform, and therefore the field lines are parallel and equidistant. So keywords: Earth is a huge magnet, there are magnetic field lines, and the magnetic field is uniform over the limited space. So they are normal to the Earth near the poles and parallel to the Earth's surface near the equator. So when we plot Earth's magnetic field lines, they will be parallel, a set of parallel lines. Look at 10.7. Parallel lines of uniform magnetic field. So they do not intersect each other, they are parallel to each other, equidistant from each other, from geographical north to geographical south. Now, plotting of field lines of a bar magnet. Very important. 10.8, draw. So you see the arrows are also very important. Okay.
Yes, ma'am.
So please practice them and send it as a homework by first. When the magnet is kept with north facing north, then what happens? There are two conditions in which you have to plot the line. You have to do the practicals also in school. So there are two conditions. One condition when the magnet is kept with its north facing north, and when the magnet is kept with its south facing north. So this is the first condition where north is facing the north and how you get the field lines. You don't have to draw so many. 3 on either side are enough. So these 3, then यहाँ पे 3 बनाओ, नॉर्थ पोल पे 5 बनाओ, साउथ पोल पे 5 बनाओ, इधर साइड में 3 दें. Okay? Yeah, 2. That's also okay. So this is how you get. And these X points, which are marked along the equator, are the neutral points. Here, Earth, there is zero magnetic field. Why? Because Earth's magnetic field and clashes with it and nullifies the magnetic field due to this bar magnet. So there is zero magnetic field. Okay. Again, draw this two times. Now, the magnetic field lines are curves in the vicinity of the magnet. At distant point, the field lines become parallel, which may be due to Earth's magnetic field. There are 2 points equidistant from the center with X in the east and west, and these are the neutral points, as I told you. Now, this is the condition when south of the Earth's magnetism is facing the south of the artificial magnet is facing. So again, you have to draw lines. These are enough. You can draw only this much. And you see that X and X, the neutral points are along the axis. Neutral points are along the axis. In the other case, the previous case, the neutral points were along the equator. So when the magnet is kept with its south facing north, the magnetic field lines are curves in the vicinity of the magnet. At distant points, the field lines are nearly parallel, which is due to uniform Earth's magnetic field. There are 2 points equidistant from the center marked as X in the North Pole and South Pole, and these are the neutral points. So neutral points are those points at which 2 magnetic fields are equal in magnitude but opposite in direction. Equal in magnitude but opposite in direction. This is very, very important. The net magnetic field is 0 at that point. Two magnets separated by a distance, the neutral point lies somewhere between them. For a magnet standing vertical with North Pole or North Pole, neutral pole will be something neutral. Pole will be at some point axis. Sorry, North Pole facing north, it will be along the axis. North Pole facing south, it will be along the equator. For a magnet placed with its south pole facing the north, the neutral points will be equidistant from the center of the Earth's equator. Neutral points? Electromagnetism we will do next class. So please, I'm giving you 5 minutes ka break. Go through whatever we have done just now. So if you have any doubts, you can ask me. And then later on, we will move to the next. Quickly, 5 minutes, please. Any doubts?